We are told a rough plane is inclined to the horizontal at an angle alpha, where tan alpha equals 3 over 4. Okay, so a horizontal angle at alpha and tan alpha is 3 over 4. We're then told a brick P of mass M is placed on the plane. Okay, so when it says placed, it means it's not given any initial force, it's put down stationary. We're then told the coefficient of friction between P and the plane is mu. So coefficient of friction is mu and between P and the plane. We are told brick P is in equilibrium and on the point of sliding down the plane. So it is in equilibrium on the point of sliding down the plane. Brick P is modelled as a particle. So we're just going to highlight that it's modelled as a particle. And using the model, we have been asked to find in terms of M and G the magnitude of the normal reaction of the plane on brick P. Okay, so we need to find the magnitude of the normal reaction and we need to find it in terms of M and G. And this question is worth 2 marks. The first point I'm going to pick up on is when it says P is in equilibrium and on the point of sliding down the plane, what this means is the frictional force is equal to the coefficient of friction times the reaction force, okay? And this is because friction can be in 2 states. Friction can either be less than the downward force, which means the object will have an acceleration, or friction can be the same as the downward force, in which case the object will have no acceleration, okay? But in this case, because it's on the point of sliding and in equilibrium, friction is the same as the coefficient of friction times the reaction force, okay? So what I've done is I've drawn 2 diagrams off camera, just because with mechanics questions, it's always better to have it in sort of a diagram so you can see what's going on, okay? So we have our block P, okay? It can be modeled as a particle. I've drawn it as a block, so it's actually easy to visualize, but this is a point mass. We have our frictional force, F equals mu r. We have our reaction force, which is perpendicular to our plane. And we have our weight, which is at an angle to the plane, like this, okay? Now, if we look on the right-hand side, this sort of triangle I've drawn, I've actually labeled here that F equals friction, by the way. If we look here at our triangle, the reason we're able to draw this is because when we're told tan alpha equals 3 over 4, okay, we know that to find the tan of any angle, say alpha, this is, so from SOHCAHTOA, this is the opposite over the adjacent. And what this means is, it means 3 is our opposite and 4 is our adjacent, okay? So 3 is our opposite and 4 is our adjacent. And this is a classic case where the examiner won't give you the exact angle of alpha, but they'll give you enough information to work out the sine of the alpha and the cosine of the alpha, the cosine of the angle, sorry, exactly, okay? So let's proceed with solving this. Because we have been asked to find, in terms of M and G, the magnitude of the normal reaction, what we need to do is we need to find what the normal reaction is. Okay, so we need to find what R is. And the way we're going to do that is we're going to resolve perpendicular to the plane. So the first thing I'm going to write is a little note which says, resolving perpendicular to the plane, and a colon like that, okay? So this tells the examiner what we are trying to do, all right? Now, if you are given a weight of mg, what this is, so the perpendicular component is going to be mg cosine alpha, okay? And I'm going to draw a diagram now to show why that is the case, okay? First, we need to get a perspective of where alpha will fit into sort of this little force diagram we've got here, okay? If we are to continue this line all the way down, okay, the mg cosine alpha and then the horizontal component are 2 vectors which make up mg, okay? So what I'm going to do is I'm actually going to draw that down below just for perspective. So we're going to say that if we have this vector mg, because remember the force is a vector, so it's going to be mg, okay? We then have 2 components, which are the mg cosine alpha and the mg sine alpha, because this is what happens when you resolve a force, okay? So, if you were to sort of imagine this part as being the hypotenuse, what you would end up with is you could get a sort of line like that, and then a perpendicular line to, actually, let's just make it a bit smaller. So a line like that, and then a perpendicular line to it, okay? Now, it's not exact, but just imagine this is a right angle triangle like that, okay? Now we've got sort of our vertical component. So I'm just going to label this one as being the vertical and this one as being the horizontal component. Okay, so this part is vertical and this part is horizontal. All right. So if we were to try and get a perspective for where alpha should be, what we can do is I'm going to extend this line here like that to sort of mimic this part here. Okay, so this part here is what this part corresponds to, like this. Okay, and then I'm also going to draw the base just because we need our angle like that. Okay, this here is alpha. This angle here is 90 degrees. That means this angle here is 90 minus alpha. Okay, because all angles in a triangle add up to 180 degrees. Okay, from here, because we know that the vertical component is perpendicular to the plane, what that means is, it means, if I'm going to draw in green, this whole angle here, okay, as badly as it might be drawn, is 90 degrees. Okay, so we can say that this angle here is 90 degrees. Now, if we have that this part is 90 minus alpha and this whole part is 90 degrees, what this means is this part here, okay, is alpha. So we can now see that why it is mg cosine alpha, because with this as being the alpha, the vertical component becomes the adjacent angle, the adjacent side, sorry, and the horizontal component becomes the opposite. So, and the mg is still our hypotenuse, okay, so h, like that. Okay, I'm just going to put them in brackets, like that, okay? So, what we can say is, using the fact that cosine alpha, so the cosine of an angle is the opposite, is the adjacent over the hypotenuse, okay? If we are to rearrange for the adjacent, which is the vertical component, we would get that A equals h cosine alpha, and then h is mg, so A, or our vertical, equals mg cosine alpha, okay? And since we know that our vertical component of our weight is the same as the reaction force, we can say by extent that therefore R equals mg cosine alpha. Now here it's important to denote that we are not done, so I'm just going to write here vertical equals R, right? Actually, vertical component equals R, like that. But we're not actually done here, because remember the question said that we need to find it in terms of m and g, and the problem is here we have m, g and alpha. So this is where we come back to our triangle above to actually find what cosine of alpha would be, okay? Because we know that the opposite is 3 and that adjacent is 4, we can actually find the hypotenuse as being 5, okay? And this just comes from Pythagoras' theorem, okay? So what we can say is that cosine alpha, so I'm just going to write it here and say cosine alpha is the adjacent over the hypotenuse, so adjacent over the hypotenuse. This equals, so our adjacent is 4 and our hypotenuse is 5, like that. So we can say, so this equals 4 over 5, okay? And then from here we can say that therefore R equals 4 over 5 mg. Probably put another arrow here and say using cosine alpha equals 4 over 5. Just to show the examiner where you're bringing your numbers from. So this question is worth 2 marks. Your first mark comes from telling the examiner that you plan to resolve perpendicular to the plane, okay? So what we have said here and the work we've done here is enough to get us our first mark. Your second mark comes from getting that, from correctly resolving to the plane, so getting that R equals mg cosine alpha, and using the fact that cosine alpha is 4 over 5 to get R equals 4 over 5 mg. Part B has asked us to show that mu equals 3 over 4, and this part is worth 4 marks. If we want to find what mu is, okay, we need to look at which component of our force diagram takes mu into account, and the only one is this frictional force, okay? Now this frictional force only acts in the horizontal direction or which is parallel to the plane, okay? So what we need to do is we need to resolve parallel to the plane to be able to take this force into account. So that's what I'm going to say. I'm going to say resolving parallel to the plane, like that, okay? Now, in part A, I showed how you would be able to take the component mg and split it into its horizontal and vertical components, okay? But the main takeaway is that the horizontal component is the adjacent and the vertical component is the adjacent and the horizontal component is the opposite, okay? And this takes into account that this angle there is alpha, all right? So what we end up with here is that the horizontal component is mg sine alpha, okay? So what we would say is that horizontal component equals mg sine, let's just actually make that neater, sine alpha, okay? So now that we've got that the horizontal component is mg sine alpha, what we know is that because the object is in equilibrium, as we've been told in the introduction to the question, we know that the frictional force is the same as the horizontal component going downwards, okay? So what we can say is that F equals mg sine alpha. Now this is where we'll be able to introduce our mu r, because F equals mu r. So what we can say is that mu r equals mg sine alpha. We know from part A that r is 4 over 5 mg, so we can say mu times 4 over 5 mg equals mg sine alpha. Now what we can do is we can cancel both sides by mg. Okay, and this leaves us with mu equals 5 over 4 times sine alpha, because all I did was multiply both sides by 5 over 4 to get mu on this side and 5 over 4 sine alpha on this side. Now, if we are to come back to find what sine alpha is, okay, we can come back to our right angle triangle here, okay? Now, sine alpha is going to be the opposite over the hypotenuse, okay? And this comes from SO in our SOHCAHTOA, okay? So O, our opposite, is 3, and our hypotenuse is 5, okay? So what this means is that this equals 3 over 5, okay? So what I'm going to do, I'm going to draw a little arrow and say here that sine alpha equals 3 over 5, which is what we just worked out here, okay? And then what we will end up with is that mu equals 5 over 4 times 3 over 5. We will cancel both of these 5s, and then we are left with mu equals 3 over 4, and we can say as required because this was a given result. So this part is worth 4 marks. Your first mark comes from informing the examiner that you are trying to resolve parallel to the plane. Your second mark comes from using the fact that the block is in equilibrium, and that means that the frictional force F equals mg sine alpha. Your third mark comes from using that F equals mu r and then solving for mu, so in which case getting up until, say, here. And then your fourth mark comes from using the fact that sine alpha is 3 over 5 and that mu equals 3 over 4 is required. We have been told for parts C and D that we are not required to do any further calculations. We are told brick P is now removed from the plane and a much heavier brick Q is placed on the plane. Okay, so by being placed, there is no external force, only the natural ones. Okay, we're then told the coefficient of friction between Q and the plane is 3 over 4. And we've been asked to briefly explain why brick Q will remain at rest on the plane for 1 mark. Okay. When you are looking at remaining at rest, you are looking at the friction being limiting. So we can say limiting friction. And what this means is that F equals mu r. All right, so that's where we will start with. We'll start with that F equals mu R. We will then come to get F equals mu mg cosine alpha from the fact that R equals mg cosine alpha. We will then say that mg is our weight. So we will say that this becomes weight times mu cosine alpha, okay, where mg equals our weight, and I'm just going to write it out here like this, okay. Mu cosine alpha is a constant, okay, so what we will say is that this becomes F equals k times our weight, where k is a constant, okay, so we'll just say that k equals mu cosine alpha, and we're going to write in bracket constant, like that. And then from here, what we can say is that F is therefore proportional to our weight, okay? So I'm just going to say that this is proportional, like that, okay? And I'm just going to link this to our proportional symbol here, just so you don't get confused between that and omega, and alpha, sorry, okay? So from here, what we'll say is that friction is proportional to the weight component, is proportional to the weight component, okay? This is sort of the translation between the mathematical language and the language we're going to have to write our final answer in, okay? So then what we're going to say is, this means that friction will increase by the same proportion as the weight component, Okay, for this you get 1 mark for any correct answer. Again, we're told for parts C and D, we are not required to do any further calculations. Brick Q is now projected with a speed of 0.5 meters per second down a line of greatest slope of the plane, okay? So this just means it is going down the plane. Brick Q is modeled as a particle, okay? Using the model, we need to describe the motion of brick Q, and we need to give a reason for our answer for 2 marks, okay? So previously, we were told brick Q is an equilibrium, okay? So we say brick Q has, let's just fix that, has no resultant force, okay, down the plane. We can then say no resultant force means no acceleration. And we can actually write in brackets that this comes from F equals ma, okay? So if F is constant, if F is 0, then that means A has to be 0 because the brick has a mass, so the mass can't be 0, okay? From here, what we can finish by saying is, therefore, brick Q slides down the plane. So slides down the plane with constant speed. Okay, I'm going to underline constant because that's the key word. So for this part, you get 2 marks. Your first mark comes from describing the motion of brick Q. So that is this line down here. And then your second mark comes from explaining why that is. So the fact we said no resultant force and therefore no acceleration will get us our second mark. So getting either of these lines will get you your second mark.